that means that the estrogen receptor binds beta-estradiol 1,000 times better than testosterone, right? And this is on purpose. It has evolved to be this way. We don't want an estrogen receptor responding to testosterone or signals we get crossed. And how are enzymes able, or receptors in general, able to distinguish between such similar compounds? Well, this comes down to the concept of an active site, which we'll revisit again on Friday. But the active site in an enzyme is where a chemical reaction is catalyzed. The active site in a receptor is where a ligand is bound. Okay? We remember from our chapter 2 discussion, right? We have a three-dimensional structure of a protein. Okay? So we start at the N-terminus and end at the C-terminus down here. And all these alpha helices, beta loops, beta terns, all these come together and interact to form the tertiary structure, in this case, the estrogen receptor. Here is where estrogen binds, right? So notice that we have a couple of beta strands, a couple of alpha helices, not necessarily next to each other in the primary sequence, but close to each other in the tertiary structure of the estrogen receptor. So if we look at just the amino acids that are lining this pocket here, this active site, what we see is we have an asparagine up here, phenylalanine, a leucine down here, right? So we have all of these residues, which are all part of, say, this alpha helix and this alpha helix and this beta strand, right? All in the active site. And they're positioned that way on purpose, right? The main purpose of the rest of the structure here on, in this case, the estrogen receptor, is to position these residues in the active site in this specific way so that they can make weak interactions with their respective ligand. And those weak interactions are going to be maximized when it's the correct ligand in the active site. So here we have, again, beta-estradiol. It's making weak interactions with the asparagine here. Notice we have a hydrogen bond donor and a hydrogen bond acceptor here. We have this phenylalanine, which is providing van der Waals interactions between the rings. We have, again, a hydrogen bond donor and a hydrogen bond acceptor here. These interactions all add up such that we have this L50 of about 1 nanomolar. Now, if we try the same thing with testosterone, right, it will still be able to fit in the active site, right? It's about the same size. It's made up of roughly the same number of atoms. So it's not going to be inhibited from going in just from being too small. But instead, it's not going to bind as well because it doesn't form the correct weak interactions with all of the residues lining the active site here. So the chances of that happening are lower because there are fewer interactions happening. On top of the fact that, again, if we look at the structure of testosterone, right, we see that it is slightly thicker because of that kink, so it will have slightly a harder time fitting in here, okay? So they're roughly the same size, but even this very small change in size is enough to exclude a lot of the testosterone. Even the one that does get in forms poor interactions with all of the residues lining this pocket here. Now, ligands also have to disassociate from a receptor, okay? So we can't have a receptor that binds a ligand and then that's it, because that is the end of that receptor. What we need is a receptor that binds the ligand, initiates some signal. We'll talk about signal transduction later on, but we need a way for that signal to be turned off, or we need a way for an enzyme to release its substrate after the reaction has been catalyzed, right? So we actually have something that looks like this. We have a receptor plus a ligand, which leads to a receptor-ligand complex. This receptor-ligand complex can then dissociate to yield receptor and free ligand again. This free receptor can then bind another ligand, form another receptor, on and on. So at equilibrium, right? What do we know about equilibrium? What's happening at equilibrium? There are two kind of correct answers, yes.
It's dynamic, so it's constantly switching back and forth between the two states.
Constantly switching back and forth between the two states, correct. And at what rate is it switching back and forth between the two states? The same, it's equal. So we can say that, yes, at equilibrium, all of these are switching back and forth between each other, but they're switching back and forth at the same rate. So what we can say is that at equilibrium, actually nothing is happening, all right? Nothing is happening, meaning that at equilibrium, the rate of association and dissociation are the same, and so the concentration of all three species remain the same, okay? So we can describe binding propensity or fractional saturation quantitatively, so in number terms, right? So let's look at this first example here. For the ligand binding reaction, R receptor plus ligand yields RL complex, so they're bound together. The equilibrium for this constant is easy. It's just K equals product of the reactants, which is RL over R times L. And we call this something special. We call this the association constant. Now this is where things get kind of weird, right? So this Ka is not the same as the acid dissociation constant that we talked about in chapter 1. This is the association constant for a receptor and ligand. So try to keep that in mind. You have to use context clues to figure that out, right? But anyway, if we talk about the acid dissociation constant, the equilibrium constant Ka, right? Because this is an association reaction, and the units here are 1 over molar, right? So molar cancel with molar, leaving us with 1 over molar. This is kind of annoying, right? 1 over molar. What does that actually mean? Well, it's kind of a pain in the ass, and I don't want to deal with it, right? So Ka is kind of not a very useful constant that we deal with in biochemistry. Instead, what we deal with is the dissociation constant, which is simply 1 over Ka. And why is that? Well, if we look at the previous reaction, R plus L yields RL, we have another reaction going on here, RL yields R plus L. So if we do that, RL yields R plus L, the equilibrium constant here is K equals R times L over RL, okay? So what does this get us, right? Well, this is a dissociation constant because the reaction that we're dealing with here is a dissociation between R and L, and here the units are molar, right? Molar cancel with molar. Sorry, there's an extra bracket here, so don't let that confuse you. Molar cancel with molar, okay? And we're left with molar on top. So now we have a constant, Kd, which is in units of molar, and this is more easier to understand. We know what molar means, right? So what is Kd then describing in terms of binding capacity? Well, when the ligand concentration equals L50 or L half, right? So when we're here, then Kd equals whatever concentration that is. So in effect, right, Kd is L50, right? Why is that? Well, Kd again equals R times L over RL, right? So if we say that L equals 1/2, L equals L 1/2, what we end up with is RL times L half divided by RL, which gets us L 1/2, right? So how did we come up with this equation, right? Well, let's start at the very beginning, okay? In general, the concentration of free receptor and free ligand aren't known, okay? So we come back here to our reaction here. Free receptor and free ligand aren't known, and really neither is RL here, okay? But what we do know is the total amount of receptor that we added and the total amount of ligand that we added, right? So we add, 0.5 millimolar receptor and 2 millimolar ligand. We know what that is, right? So can we do something with that? Well, if we say that our total must be equal to the number of free receptors plus the number of receptors in a complex, well, that makes sense. There's nowhere else for the receptor to be. So our total, which we know, must equal free receptor plus however much complex we have. And the same is true for L total, right? The total amount of ligand that we add must be equal to the total amount of ligand that's currently in a receptor plus the amount of ligand that's floating free in the solution. So if we rearrange this, we can solve for free receptor and free ligand, just saying that R total minus RL, or R total equals R total minus RL, and L equals L total minus RL. So now we can rewrite our Kd equation. Remember, Kd equals R times L over RL. So if we know that R is R total minus RL, and L is L total minus RL, divided all by RL. So now we only have the RL to worry about. R total we know, and L total we know. Now we can kind of cheat a little bit. Oh, wait. Oh, I just skipped that. Oh, wait, sorry. So here we have Kd, right? And now we can cheat a little bit. We can say that generally what's observed is the amount of ligand that's part of an RL complex is very small compared to the total amount of ligand that we added, right? So that means that RL is much less than L total, meaning that L total minus RL isn't equal to L total, obviously, but it's close enough, right? So we can say that L total minus RL is approximately equal to L total, simply because RL is so much less than L total. So we can now sub that in for our L total minus RL and say then that our equation simplifies down to R total minus RL, right, times L total minus RL, which is really just L total divided by RL. Now we can distribute this out into here, cancel out the RLs that are left over, and what this simplifies down to is R total times L total over RL minus L total equals KD. Now, we rearrange, right? So we add L total to both sides, leaving us with KD plus L total equals R total over L total divided by RL. We do cross multiplication, and we see that RL divided by R total equals L total divided by KD plus L total, right? And what is RL divided by R total? Well, what's RL telling us? Just in general terms, in English, what is concentration of RL? Concentration of the receptor bound to the ligand. And what's R total? The total amount of receptor available. So what is this telling us about the binding? Amount that is bound divided by total amount. What is that going to be? It's a percentage. We call that the fractional saturation, right? We can have it go anywhere from 0 to 1, right? Or 0 to 100%, right? So the fractional saturation is just equal to the ligand concentration divided by the ligand concentration plus KD, and we can see now why we can never be at 100% saturation. Okay, we can never be at 100% saturation because 100% is 1, which means that L total over KD plus L total must be 1, meaning that these must be the same, okay? But they can't be the same because otherwise KD would have to be 0. And it can't be 0 because otherwise it would be infinite binding, which is not possible. So we can add L total until we get to 99.999%, but simply by the fact that KD cannot physically be 0, right? Chemically and physically, this can never be 100%. We can never have 100% binding. An easier way to understand fractional saturation is just to look at our association reaction here. R plus L yields RL. Ka is RL over R times L. Kd is RL over R times L over RL. We can say that Y, the fractional saturation, again, is sites occupied divided by total number of sites. Sites occupied, of course, is RL divided by R total, which must be RL plus R, right? Now we can substitute RL for Ka times R times L, right? So multiply R times L by this, and we get RL. So we say that RL is Ka times R times L divided by, again, Ka times R times L plus R. We can factor out Ka times R, leaving us with this, Ka times RL, that's the same, Ka times R times L, plus 1 over Ka, right? So these two are the same, but now we can cancel out the KARs, leaving us with L over L plus 1 over Ka, is our fractional saturation. Of course, 1 over Ka is Kd, so fractional saturation is L over L plus Kd, which is the same thing that we derived on the last slide. So now we're able to determine how much of our ligand is saturated. And this is true when this process is correct, right? When this is the process, 1 receptor plus 1 ligand yields 1 complex. So see, when we talk about hemoglobin, this isn't always the case. Hemoglobin is able to bind 4 O2s, right? So our reaction here becomes R plus 4L yields RL sub 4, right? For that, we have to take into account the stoichiometric coefficients, right? And we'll see what that looks like later on. All right. So again, now when L equals KD, right? What does that mean? Well, when L equals KD, everything here simplifies down to 1/2. So we can see now where we got that 1/2 before and what KD means. So what does this mean for binding then? What is KD describing? KD is basically describing L50. It's describing what concentration we need to reach before we get 50% saturation, right? And again, this is where we find usually the physiological concentration of L. Kd will be like L50 because they're describing the same thing, is telling us more or less what the physiological concentration of the ligand we're typically going to encounter, right? We see that down here. L1/2 equals Kd. Here we have example binding. When L1/2 equals Kd, we can follow that up and see that we get to exactly 0.5, right? So now let's look at a couple concrete examples of binding, right? Myoglobin first and then hemoglobin. Hemoglobin is actually very interesting because it also touches on a few other types of binding regulation that myoglobin doesn't. All right, so here what we're looking at is a fractional saturation curve. Why? Though now instead of L being L, it's going to be O2. And because O2 is a gas, we're not going to measure it in molar, we're going to measure it in torr, right? So we're looking at the partial pressure of oxygen in the atmosphere, okay? So we go from 0 torr to a little bit over 100 torr. In the lungs, right, you should know this, in the lungs, the typical concentration of O2 is about 100 torr. In exercising muscles, the PO2 is typically about 20 torr. And in resting muscle, the PO2 is about 40 torr, right? And this is all going to be important once we start talking about hemoglobin, right? So essentially, right, what percentage of myoglobin is bound to oxygen at different concentrations is shown here as fractional saturation. The P1/2 or P50, in this case we're calling it P instead of L because we're measuring pressure, okay, is 2 torr, right? So after the partial pressure of oxygen passes 2 torr, we're now at 50% saturation. Anything above that is going to be more than 50%, which presents a problem, right? Why? Okay, well, let's look at the lungs, right? So we breathe in, right? We're going to be at up here. So what percentage is that? I have to do all the math, but roughly. Yeah, about 100, 99%. It can't be at 100, so let's call it 99%. Now let's go down to exercising tissue. Let's go to resting tissue, right? What's the fractional saturation here? Well, maybe like 96, 95%. So we've only delivered about 3 to 4% of the oxygen that bound to myoglobin in the lungs. So myoglobin is an especially bad oxygen carrier because it can bind oxygen very well, but it's very bad at getting rid of oxygen, right? Because it's got such a low P50, right? Or P1/2, 2 torr. So no matter where we are in the body, right, we're going to be above 20 torr. We're not going to be delivering really hardly any oxygen. So if we look at myoglobin, right, so myoglobin is made up of 8 alpha helices, right, labeled A, B, C, D, E, F, A, B, C, D, E, F, G, H, right? So A through H, and importantly, it's got what we call a prosthetic group. Now we haven't seen a prosthetic group before, but the reason we call it a prosthetic group is just like, you know, a prosthetic limb, right? It helps the enzyme function. In fact, in this case, and in any case with a prosthetic group, the enzyme cannot function without the prosthetic group. And the prosthetic group is not part of the primary, secondary, tertiary, or quaternary structure of a protein. It's not an amino acid polymer at all. It's something else entirely. In the case of myoglobin and hemoglobin, the prosthetic group is what we call heme. Right? And heme is made up of 2 parts. It's made up of a protoporphyrin. You see here, right? These 4 rings arranged in a circular pattern. So this protoporphyrin, specifically protoporphyrin 9. We'll see more about protoporphyrins when we talk about amino acid catabolism. But in addition, we need the iron in the center, right? So this protoporphyrin plus the iron in the center gives us a fully functioning heme. It's the iron in the center of the heme that is going to be binding oxygen. And so without heme, myoglobin or hemoglobin is unable to bind oxygen. Oxygen will only bind to this iron. Now, weird thing about iron is, well, not weird, it's a metal, right? But the annoying thing about metal chemistry is that we're dealing with coordinate covalent sites. In this case, we have the first 4 coordinate covalent sites all bound to the nitrogens at the ends of these chiral rings, right? There's a fifth and a sixth coordinate site as well, above and below. So there's one coordinate site facing away from you in this orientation and one facing towards you in this orientation. The fifth coordinate covalent site is bound to a histidine, right? It's bound to a histidine on the F helix of myoglobin. So here we have a histidine that's part of the F helix, right? So either this one or this one, right? One of these two is the F helix, and that's got a histidine that protrudes out. Remember, the functional groups of the residues in an alpha helix stick out, right? So these will be sticking out towards either from here or from here towards the heme. And when that happens, the histidine now occupies the fifth coordinate covalent site of the iron in the center of the heme. Now, in this state, right, iron is in its ferrous oxidation state, so it's Fe2+, right? This ferrous iron, Fe2+, is too large. The van der Waals radii is too large to physically fit inside the hole left by the tetrapyrrole, by protoporphyrin 9. So it sticks out, it's got a pucker. Once oxygen is present, right, oxygen will now occupy the sixth and final coordinate covalent site of that iron. And because oxygen is electronegative, right, this iron converts from the ferrous state into the ferric state, Fe3+. When this happens, its effective radius shrinks. The van der Waals contact distance is less and is now able to fit inside of the pore of the protoporphyrin 9. Right? So what happens? We go from a puckered to an unpuckered configuration. When this happens, the iron shifts up, obviously, but doing so also pulls up on this histidine. And because this histidine is part of the F helix, that histidine being pulled up also pulls up on the F helix. Okay? This induces a conformational change in myoglobin. Now, in myoglobin, this really doesn't matter at all. Okay? But as we'll see when we talk about hemoglobin, pulling up on that histidine, right, does something interesting. Again, pulls up on that helix, and that helix communicates to other parts of hemoglobin, and it makes those other parts of hemoglobin more susceptible to binding oxygen. Right? Again, don't get too bogged down with that right now, but here, again, when oxygen binds to Fe2+, it becomes Fe3+, and so what we have effectively is a resonance structure that we see here, all right? We have O2 binding to Fe2+, but we can think of it also as an O2 minus superoxide in the sixth coordinate covalency of an Fe3+, right? And so enters the distal histidine. This first histidine that we talked about, we call this the proximal histidine, right? The distal histidine is on the other side of the heme, okay? So here down below, right, we have the fifth coordinate covalent site binding with the histidine, the proximal histidine on the F helix. Here we have the distal histidine on the opposite side. Once O2 binds, right, it's a superoxide, so that negative charge is also electronegative, and this is in close proximity with this histidine here, right, the distal histidine. So what kind of interaction are we able to form? It's a weak interaction. What kind of interaction is that?
Ionic.
Could be ionic, right? If we say that this is O2 minus and this is NH plus here, it could be ionic. Could also classify this as a hydrogen bond, right? With oxygen as the acceptor and NH as the donor. The point is that the distal histidine stabilizes O2 binding here, right? It forms this interaction, which is now favorable. So it makes it harder for that O2 minus to leave. And this is important for a couple of different reasons. O2 minus, right? How would you classify that as a molecule, right? It's got a specific name. It belongs to a class, it belongs to a species, right? What is O2 minus? It's in the same category as peroxides, radicals. They're called reactive oxygen species, ROS. If O2 minus were to dissociate from this hemoglobin in this state, well, now we have O2 minus floating around. O2 minus, because it's a reactive oxygen species, as the name implies, will react with pretty much anything that it comes in contact with. Proteins, DNA, RNA. right, changing them, and we don't know how they're going to change them. So it's in the interest of the cell to make sure that O2 minus doesn't leave. One of the ways that it does that is by having this distal histidine here, stabilizing the interaction between O2 and this iron here. Second, if O2 minus were to leave, that leaves hemoglobin in the ferric state, in the Fe3 plus state. Fe3 plus cannot bind O2, right? It can bind O2 in the 2 plus state and become 3 plus, but if we have Fe3 plus to start with, this can now no longer bind oxygen, right? It's got one less electron, so we have one less coordinate covalent site to occupy, all right? This is called methemoglobin. When we have hemoglobin that is stuck in the Fe3 plus state, that's methemoglobin, and that's a dead-end hemoglobin. Now the body has mechanisms to convert methemoglobin back into hemoglobin, which is to say to reduce Fe3 plus back to Fe2 plus. That's done by cytochrome B5 reductase, right? But there's a limit to how much that enzyme can do, right? So we might be able to overwhelm that. Additionally, have you heard about this family in Tennessee or Kentucky, the Fugates? Have you heard about the Fugates? The blue people, yes. They have a condition where they're deficient in cytochrome B5 reductase. So while our body naturally produces a little bit of methemoglobin every day, right, that's easily converted back into hemoglobin by cytochrome B5 reductase, okay? But they're deficient in that. So the methemoglobin that they produce remains. And methemoglobin, because it's in the 3 plus state, is oxidized and it is blue, right? So they have a blue complexion because they aren't able to remove that methemoglobin. It is possible to treat it using methylene blue, and methylene blue aids cytochrome B5 reductase so that they can convert that methemoglobin back into hemoglobin. But without intervention, yeah, you just remain blue. All right, now the downside of using iron, though, right, is that it can bind other things as well, right? So iron intrinsically has a high propensity to bind carbon monoxide. So here we see heme, all right, proximal histidine on the bottom. On the top we have the 6 coordinate covalent site, now not bound to O2, but instead bound to carbon monoxide. The P50 of carbon monoxide is 0.02 torr. And remember, the P50 for O2 is 2 torr, right? So carbon monoxide binds hemoglobin, or myoglobin rather, 100 times as strongly, right? Binds myoglobin 100 times stronger than O2, right? And because it binds so strongly, it's virtually impossible for this myoglobin to release the carbon monoxide, which is why, you know, if you have in my house we have natural gas heat, right? So what we have to have is a carbon monoxide detector. It's odorless, and very small amounts is able to very quickly outcompete oxygen for binding of myoglobin or hemoglobin, right? Now there is a treatment if you don't die first, and simply to outcompete the carbon monoxide, right? So we have a little bit of carbon monoxide that can outcompete the normal amount of oxygen that we encounter every day, right? But we can actually outcompete carbon monoxide using oxygen just by hyperbaric treatment, right? Which is to say, instead of, you know, the 18% oxygen that we find in the atmosphere, if you administer 100% oxygen, right? It's dangerous to do just every day. But now if you increase the effective concentration of oxygen, you are able to outcompete carbon monoxide for binding of myoglobin and hemoglobin. All right. Now, how can we make it so that oxygen is bound in the lungs, but released in the tissues? Because again, remember, right? Here we have the loading curve for myoglobin, right? It's got a P50 of 2 torr and a P50 of 2 torr. So let's do the math here real quick and see how much oxygen could be delivered by myoglobin in the lungs and then in exercising tissue at 20 torr, right? So let's do a quick kind of calculation here. We'll say we want to find first fractional saturation at 100 torr, so we'll call that Y100, minus the fractional saturation at 20 torr, Y20. right? So let's say 100 torr divided by 100 plus kd, which is 2, right? So this is L over L plus kd, which is 100 over 100 plus 2, minus 20 over 20 plus 2. So 100 divided by 102 minus 20 over 22, right? So what does that come out to? Well, not very much. %, right? So easy calculation. We can see that we can only deliver 7%. Now 7% is insufficient, right, to sustain life. We need to deliver way more oxygen. Oxygen serves as the final electron acceptor in the electron transport chain. We'll get to that in chapter 18. But we simply cannot generate enough energy to sustain all of our systems without oxygen. We can generate energy without oxygen, but not enough. Certain bacteria can generate enough oxygen, or enough energy rather, without oxygen to remain alive, but we cannot. We need oxygen. 7% delivery is simply not enough, so we will suffocate. So we need a new way, we need a better way to deliver oxygen, right? So again, myoglobin is very good at binding oxygen. We find myoglobin in the muscles, right? So it binds oxygen and it steals it for the muscles, which is where we need the most energy. But it's bad at taking oxygen from the lungs and then releasing it once it gets to the tissues. For that, what we need is what? Well, one thing that we could do, right, is to shift this entire curve to the right, right? If we shift it to the left, then we have that tight binding situation. If we shift it all the way to the right, then we have that weak binding situation. We could alter myoglobin such that it delivers a decent amount of oxygen, right? Now, as it turns out, even that is not enough. Even if we do, and we'll see an example, we'll see not the calculation, but we'll see the end result of the calculation, the theoretical maximum oxygen delivery that we get just by shifting this curve over is also high. What we need is something a little bit more complex. And this is hemoglobin, right? So hemoglobin is a complex of 2 alpha chains and 2 beta chains. So it's a heterotetramer. And it's best to think of hemoglobin as a dimer of dimers, right? So we have an alpha beta dimer in a dimer within another alpha beta dimer, right? So we have 2 alpha beta dimers stuck together. The reason that this is a better way to think of it, we'll see when we talk about the transition between T to R state of hemoglobin. Now, each chain on its own is useless, right? So this is the example of tertiary and quaternary structure from chapter 2. Each alpha chain and each beta chain has its own tertiary structure, but they are not used as oxygen carriers, right? It's only when the quaternary structure, these 4 individual polypeptide chains come together to form hemoglobin that we get the characteristics of hemoglobin that are necessary to deliver oxygen, as we'll see. Each chain also binds its own heme, right? So each chain, each subunit of hemoglobin can carry 1 O2, right? In other words, one hemoglobin molecule, one hemoglobin protein can carry 4 oxygens at a time, right? So if we look at the loading curve for hemoglobin and myoglobin, you see they look radically different, right? First, as we suspected, okay, a good way to deliver more oxygen is just to take the myoglobin loading curve and shift it down to the right. But in addition, look down here, right? What we have is not a hyperbolic loading curve like myoglobin has, right? So that fractional saturation Y equals L over L plus KD, right? If you graph that in your graphing calculator or on Desmos or whatever, you'll see that that's always hyperbolic. It starts out vertical and then reaches an asymptote. Hemoglobin's loading curve, though, is what we call sigmoidal, right? It starts off slow and then increases and then levels off, right? This is indicative of an enzyme that is cooperative, right? It's a cooperative protein. And what that means is that different parts of hemoglobin work together cooperatively to bind oxygen, right? In short terms, right, we'll see this better in a couple slides. The first oxygen that binds hemoglobin is slow to bind. It's got very low affinity for oxygen. The next one that binds has a slightly higher affinity. The third one that binds has a higher affinity, and the fourth one that binds has the highest affinity. Right, so the first oxygen to bind is slow, and then it speeds up, which gives us this characteristic swoop down there, right? We also see sigmoidal loading curves in enzymes that are allosterically regulated, which hemoglobin is. We'll get to what allostery is in just a second here. But by virtue of both being shifted to the right and being sigmoidal, we're now able to deliver much more oxygen, right? So in the lungs, again, at 100 torr versus 20 torr in exercising tissues, we're able to deliver 66% of the oxygen, right? 66% oxygen delivery. At rest, right, we can deliver 21%. Well, that's interesting, right? This sigmoidal loading curve aids not only in delivering more oxygen, but in responding to the oxygen needs of different tissues. Hemoglobin has evolved such that it knows, it doesn't know anything, but it reacts to 20 torr by delivering sufficient oxygen for exercising muscle. But when it encounters, say, 40 torr, well, that's a muscle or a tissue that isn't under stress, so doesn't need as much energy, and so doesn't need as much oxygen. So it won't deliver as much, and instead holds it until it encounters the tissue that does need it, right? So it's able to deliver oxygen specifically to the tissue that need it. If we look over here again, 7%, that's just what we calculated before. That's how much oxygen could be delivered by myoglobin, right? We got 7.1, they got 7%, so that's pretty good. Hemoglobin, again, delivers 66%. So why did evolution select for this more complex loading curve, right? And this more complex structure, which requires 4 different polypeptide chains? Well, it's because the theoretical maximum that we can get, no cooperativity, so basically a myoglobin that has been optimized to deliver as much oxygen as possible, could only ever deliver as much as 38%, so a little bit more than half of what hemoglobin is able to deliver in real life, right? So again, in the best possible situation, we would not be able to deliver as much oxygen as hemoglobin can. In fact, 38% oxygen delivery is not good enough for exercising tissue, right? Additionally, it's not able to effectively respond to the needs of that specific tissue. If we look over here, at 20, we're here, but at 40, we're only over here. That's a difference of maybe 5 to 10%, right? So it's simply not enough response to the needs of different tissues and different stress conditions, and not enough overall oxygen delivery at all. All right, so now let's look at how hemoglobin binds oxygen, because it's not as simple, obviously, as myoglobin binding oxygen, where it binds and forms an RL complex, and we're done. Hemoglobin exists in 2 states, a T state and an R state. The T state corresponds to what we call deoxyhemoglobin, and the R state corresponds to what we call oxyhemoglobin. The T state, deoxyhemoglobin, has very low affinity for oxygen, while the R state has very high affinity for oxygen. In fact, the loading curve for the R state looks almost exactly like the myoglobin loading curve, so it's got a very high affinity, whereas the T state binding curve has very little affinity for oxygen. So what we see is that kind of weak binding situation that we had before. So in reality, right, we don't have either the R state binding curve or the T state binding curve, but we have something in between, which means that the R state and the T state don't really exist all the time, right? What we get is this constant switching back and forth between the R and the T state. When hemoglobin switches from the T state to the R state, notice what happens here. Why we're considering hemoglobin as a dimer of dimers. This alpha beta dimer twists counterclockwise by about 15 degrees relative to the other alpha beta dimer. Right here, the alpha is in pink and the beta is in yellow. Right? So here, this alpha beta dimer rotates, and when it rotates, this pocket or this pore that is formed at the interface between the 2 dimers closes. And this is important in the regulation of hemoglobin, as we'll see, right? But when we switch from T to R, we rotate 15 degrees, and what determines how hard it is, or partly what hard it is to go from T to R, or from R to T, is this pocket here, as we'll see, right? So, how do these 4 oxygens load on this hemoglobin? Well, the answer is that we're not really sure, right? There are 2 models that partially explain it, but neither model completely explains it. So what's likely going on is some in between, some mesh between the 2 models. And what we have here is the concerted model. And the concerted model explains O2 binding specifically at high occupancy, right? So let's look at what's going on here. So we have the 4 subunits of hemoglobin, right? 1, 2, 3, 4. This is all the same hemoglobin molecule, just in different states, right? We have T, or rather T over here, and we have R as the circle. So T state subunits are squares, and R state subunits are the circles. So initially, when we have no hemoglobin, right, the T state is strongly preferred because we're deoxyhemoglobin. So we have an equilibrium between T and R where T is strongly preferred over R. That's not to say that there are no R, right, but T is preferred. Now, if we look at just the T configuration here, well now, this can bind oxygen, but very slowly, right? It can bind oxygen, but the equilibrium lies far to the side of T, or to the side of the no oxygen bound. Whereas the R really wants to bind oxygen, right? Because that's got a higher affinity for oxygen than you see over here, right? So what happens? Eventually we will bind an oxygen, not via necessarily the T, but by the R, right? Which is still present, but at lower amounts, obviously, than the T, since it's not preferred. But we will get here. Now, once we've bound the first oxygen, now the equilibrium changes. So the equilibrium doesn't as strongly favor T. Instead, it favors a little bit, it still favors T, but not as much, right? So we have more R relative to T. Now the equilibrium going from either one of these to the next is the same as it was before, right? But now because we have more R, we can get more over here. So going from this state to this state is slower, right? It was slow. Going from this state to this state is now a little bit faster, meaning effectively that second oxygen is easier to bind. The same principle holds true. Going from here to here is now easier because we have, again, now more R than we had here, right? Which means we have more R than we had here, so we can get to here a little bit faster. Now we're strongly favoring the R, and we get from here to here even faster, right? So we see that the first oxygen that binds to deoxyhemoglobin, which is mostly in the T state, right, is slow because it has to find an R state effectively, which isn't very prevalent. But once we do, now we have more R state, which means that it can bind the next oxygen sooner, and then sooner, and then soonest, or sooner, until we get to a fully R state oxyhemoglobin, right? The other model is the sequential model. And this best explains oxygen binding at low occupancy, right? Reason being here, why it explains at high occupancy, is all of this makes sense, right? But here, going from this to this, seems like it would just take too long, right? So that can't be the whole story. At low occupancy, the sequential model makes more sense, right? In this case, all right, what we have are 4 T state subunits, okay? But here, instead of the entire hemoglobin being only either 4 subunits in the T state or 4 subunits in the R state, instead what we have is each subunit able to adopt either individually R, T, or some in-between state, right? So here in completely deoxyhemoglobin, the first O2 that binds is slow, right? But that changes this from the T state to the R state, right? It changes from the T state to the R state. And it communicates that change to nearby subunits. So now this is not interacting with this, right? But these two are. So these get changed from the T state into kind of an in-between R/T state, which make it easier for these two to bind. This one remains unaffected. So the next oxygen that binds is able to bind a little bit easier, right? Because here there's not in the T state anymore, it's in an RT state. The next one that binds, now these two are making contact with these two, right? So these are now both in an intermediate state, meaning that either one of these could bind oxygen better than it was over here. So we get the third one binding, and then of course now we get the fourth one binding. The reason here, this explains it best at low occupancy, is that we consider this situation here, right? Well, would this bind better? Would this bind better? Because it's making contact with 2 R state subunits. So would this be more R than T, or is it strictly RT? That's not clear either, but what is explained better is binding at low occupancy here. So what's really going on is probably something in between. The jury's still out, right? We've been studying hemoglobin since the early 20th century, and it's still not completely understood. All right. So how do these different subunits communicate? Here it is clear that they communicate, right? Also here they communicate. How do they communicate? Why is that necessary? Well, remember, hemoglobin binds oxygen cooperatively, meaning that the first oxygen that binds has to somehow tell the rest of the enzyme or the rest of the protein, hey, we bound the first oxygen, so the next one should be easier. How is that accomplished? That's accomplished again via this proximal histidine. So if you remember from myoglobin, we had the proximal histidine at the 5th coordinate covalent site under the heme. On the other side, O2 is bound at the 6th coordinate covalent site. Remember, I told you that that histidine gets pulled up by Fe2 plus being oxidized to Fe3 plus, right? But in myoglobin didn't really do anything. Here, it does something, right? This histidine, exactly the same way that it was in myoglobin, is pulled up because when O2 binds to Fe2 plus, it's oxidized to Fe3 plus, it shrinks, it unpuckers the heme, pulling up on the iron, which pulls up on the proximal histidine, which now pulls up on the F helix, right? This F helix lies at the alpha-1 beta-1, alpha-2 beta-2 dimer interface. So it lies at the interface between those two alpha-beta dimers. When this helix moves, right, that movement can be sensed by the other dimer. And it changes the conformation of that dimer, right, to likely load oxygen a little bit easier. It makes it easier for the next oxygen to load. So they communicate via the movement of the F helix. And the F helix moves when O2 binds that first heme. Now over here, right, at the rest of the alpha beta dimer on the other side, now we have those hemes which will bind oxygen, pull on their F helices, which are in contact with the other alpha beta dimer, right? So it gets easier and easier as it goes, right? So it's the movement of this helix that promotes the communication and allows for cooperativity. Now, cooperativity alone, though, doesn't explain the hemoglobin loading curve, right? So HbA, that's the normal adult hemoglobin that we find, HbA for adult, in contrast to HbF for fetal hemoglobin, which is a different story. Right, so here, for example, what do we see? If we look at pure hemoglobin, this was actually what was found in the 60s, right? They isolated hemoglobin from human blood, right? Very good at that by the 60s and 70s. So hemoglobin was isolated. We measured the loading curve for hemoglobin. What we saw is the black line here looks almost exactly like it does for myoglobin, which we knew couldn't be the case, okay? Because otherwise, myoglobin would have just been the oxygen carrier. So what was it then that was shifting this entire curve to the right, okay? Because what we see is this loading curve in the red. Well, this has to do with 2,3-bisphosphoglycerate, 2,3-BPG. 2,3-BPG is a negative allosteric regulator of hemoglobin, right? And what is allostery? Allostery is the regulation of a binding site affinity by affecting the protein somewhere that is not the binding site. So for example, carbon monoxide would not be an allosteric regulator of hemoglobin because it binds to the same site that oxygen is supposed to bind to. That's just a competitive inhibitor, right? It competes for binding. An allosteric regulator, allos being Greek for, far away, right? It binds somewhere else on the protein other than the outer site of the binding site, and that somehow affects that receptor's ability to bind its ligand, in this case hemoglobin to bind oxygen, right? So what's going on here? Okay, here we have pure hemoglobin, right? We have pure hemoglobin, and here we have hemoglobin with 2,3-BPG. So which state is being stabilized, do you figure? Do you think the T state is being stabilized, or is the R state being stabilized? If you look at the loading curves here.
T?
Why? Well, it says on the slide that the T state is being stabilized. But looking at the curve, why is it that the T state is being stabilized? There's less oxygen?
Like the saturation for oxygen.
The affinity for oxygen.
Yeah.
The affinity for oxygen is lower. right? If we go back here, remember, here we have the R state binding curve, here we have the T state binding curve. So if we're shifting this over to the right, we're getting closer to the T state binding curve. So it's the T state that's being stabilized. If we were to shift it to the left, then the R state would be stabilized, right? And why does this matter? Well, if we shift towards the T state, are we increasing or decreasing the affinity of hemoglobin for oxygen? Is it going up or down? Going down, right? Because T corresponds to deoxyhemoglobin, right? So by shifting the curve to the right, we're stabilizing T state, the deoxyhemoglobin, meaning we're decreasing its affinity for oxygen. And we see that here. Okay, we shift it to the right, the affinity for oxygen decreases, meaning that we can deliver more oxygen, right? Because it's got a greater propensity to get rid of that oxygen. And how does 2,3-BPG do this, right? How does it stabilize the T state and shift the loading curve to the right? Right? Well, 2,3-BPG is necessary, right? It's not optional. And the reason is, again, otherwise we just have, we're delivering 8% instead of 7% for myoglobin, but really no different, right? So how does 2,3-BPG operate? Well, if we look at the structure of 2,3-bisphosphoglycerate, we'll see 1,3-BPG later and 3-PG, right? So bisphosphoglycerate, or phosphoglycerates in general, are actually very important metabolic intermediates. But in this case, 2,3-BPG has two phosphoryl groups on carbons 2 and 3 of a phosphoglycerate, right? So, or of a glycerate rather, right? So we have carbon 2 over here, carbon 3 over here. Carbon 1 has a carboxyl at the end. So what do we have? We have 2 minus, 2 minus, and 1 minus. This is an exceptionally negatively charged molecule. It's got a 5 minus charge at physiological pH. And why does it matter that we have a 5 minus charge? Well, remember when we talked about the transition state from R to T, we said that one alpha beta dimer twists about 15 degrees relative to the other alpha beta dimer. And it closes this pore, right, when those two rotate. So if we look at that pore in more detail, what we see are that the amino acid residues lining this pore are an asparagine here, a histidine, a lysine, a histidine, and another histidine here, okay? Look at these amino acids, right? This is why I told you to study those amino acids, and know their properties at least, okay? What can you tell me about lysines and histidines at physiological pH? Well, of lysines anyway, let's start with lysines. What do we know about lysines at physiological pH? They're positively charged. Histidines, in this context, right, these histidines have a pKa closer to about 7.5 to 8, right, meaning that at physiological pH, they are also protonated, meaning that they are also positively charged. Because remember, I told you the pKa's of an amino acid can change depending on the environment in which we find that amino acid. In this case, the histidine's pKa has changed such that they remain protonated. Why is this important? Well, we have now this 2,3-BPG, which is very negatively charged, in the pocket, surrounded by all these positively charged residues. Is that a favorable interaction or an unfavorable interaction? Raise your hand if favorable. Yeah, you have a positive next to a negative, so that's a favorable interaction. Okay, so removing this 2,3-BPG, what can you tell me about that in terms of energy? Is that going to happen spontaneously? No, right? We have to put in energy to yank that 2,3-BPG out and break all of these favorable interactions. And that's exactly what has to happen to go from the T state to the R state, right? This pocket collapses, is now too small to fit 2,3-BPG. Means that we have to get rid of that 2,3-BPG. We have to pull it out of here, and that's going to take energy, right? So by fitting in here into the pocket present only in the T state, it stabilizes the T state by making the energy necessary to go from T to R higher. Because not only do we have to rotate those, we have to also evict this 2,3-BPG, which is making favorable interactions with all of these. Right? So here's another thinker, okay? Let's imagine that we get rid of this histidine and this histidine on the beta chains, right? So this histidine 143 and this histidine 143 on the two beta chains. Let's say that we get rid of those. what's going to happen to the loading curve of hemoglobin? Let's take a minute. If you get rid of those histidines, what's going to happen to the loading curve of hemoglobin?
Would shift to the left,
Why?
because you're losing the positively charged amino acids there, so that there would be less
So-
affinity.
Very good. So we're losing these two positively charged histidines. So now 2,3-BPG is held in the pocket less strongly. It's going to make it easier to go from R to T, right? So if we're stabilizing, or if the T state is now not as stabilized, well now we shift a little bit to the left, right? Because now the R state is more stable than it was before, right? All right, so now we're stabilizing the R state. Now what does that mean in terms of oxygen binding? Let's see, somebody else. Higher affinity, right? So if we shift it to the right, or sorry, to the left, right? Stabilize the R state. The R state corresponds to oxyhemoglobin. Oxyhemoglobin likes to bind oxygen, so it will bind stronger. And this is what we actually find in fetal hemoglobin. That histidine 143, okay, is replaced with, what is it? A serine, right? Now, a serine is ionizable, but it is not going to have a charge, right? It's not going to have a negative or positive charge at physiological pH, meaning that that 2,3-BPG is held less strongly, making the transition from T to R more feasible, less energetically costly, right? So the T state is less stabilized, meaning the R state is slightly more stabilized, and it shifts the loading curve to the left, right? So here, fetal red blood cells, okay, they're expressing fetal hemoglobin, and the curve is predicted shifted to the left. And why is this necessary? Well, it's because fetuses are functionally parasites, right? So they can't breathe, obviously, so they have to get their oxygen from somewhere. They still need oxygen, but they don't have access to the air. So instead they have to steal it from mom. At given partial pressures of oxygen, right? When the mother's HbA comes into contact with the fetal hemoglobin will steal the oxygen away from the maternal hemoglobin, right? And this is how fetuses are able to get oxygen. Now, this fetal hemoglobin is turned off soon after we're born, right? So we don't express fetal hemoglobin, but we still do have obviously the gene for fetal hemoglobin. It's just regulated down so that it's not expressed. That's one of the ways that they're actually trying to use CRISPR to treat sickle cell anemia, is by turning back on the fetal hemoglobin gene, right? Not necessarily fixing the adult hemoglobin, but turning back on fetal hemoglobin by altering the way in which it's regulated. The Bohr effect, pH, is also a regulator of hemoglobin binding. We'll see very often that pH does affect the activity of different enzymes or the ability of different receptors to bind their ligands. So the Bohr effect basically describes that the affinity for hemoglobin for oxygen decreases at pH less than 7.4, right? So let's see what this means. So at pH less than 7.4, right? So, or actually increases the affinity, right? If we look at what's going on here, at pH 7.4, right? This is the curve that we've all gotten used to. So we deliver 66% if we bind at 100 torr and deliver at 20 torr. But as the pH decreases, what happens to the ability of hemoglobin to deliver oxygen? Can it deliver it better or worse when the pH is lower? Can it deliver it worse? Why better?
Because it's shifting right, so its affinity is decreasing, so it delivers more.
Exactly. So we're shifting to the right, okay? We're shifting to the right, so its affinity is decreasing, meaning that it wants to get rid of it so it can deliver more. And we can see that mathematically. You can plug this in, say 66% versus 77% at pH 7.2, right? And why might this be useful? Well, just like hemoglobin can deliver more oxygen to exercising tissues just by virtue of being at lower partial pressure than resting tissues, here exercising tissues are also producing a lot of what? Producing a lot of acid, right? A lot of acid from lactic acid fermentation. They're also producing acid in the form of carbonic acid, right? So CO2 is a waste product of oxidative phosphorylation, and all that CO2 is acted on by carbonic anhydrase immediately to be converted into carbonic acid, and that lowers the pH as well. So this is good for exercising tissue. If the pH is low, well, the PO2 is already low, right? If the pH is also low, now we can deliver even more oxygen, right? Way more than we could remember before. And how does the Bohr effect work? Well, just like we saw when we were discussing our pKa values for different dipeptides and tripeptides and amino acids and things like that, as the pH changes, right? As the pH changes, well, here, if the pH is low, right? This is one example. At the interface, well, actually, here, yes. Right, so at the interface between an alpha and a beta chain, and even in between two of the same residues on the same beta chain, if the pH is low, well, now this histidine, for example, might be protonated. Right, if this is protonated, well, now this can form a hydrogen bond here, a salt bridge between this histidine and this aspartate, this negatively charged aspartate. This now makes it harder for that F helix to move. And it makes it harder to communicate that change, obviously, then to the rest of the protein. So this stabilizes the R state because it makes the transition from T to R more difficult, right? By putting that kind of thing there, or more easy rather, right? So this stabilizes in the R state, okay? And this is just one example. So this histidine in the beta and this aspartate in beta as well, right? So we see an extra weak force here, but this happens all over hemoglobin. The lower the pH, the more weak interactions can occur, and so we get stabilization of the T state. All right, now carbon dioxide. Carbon dioxide, of course, we want to tell hemoglobin to deliver more oxygen. Why? Again, carbon dioxide is the main byproduct of fuel metabolism. So we break down fatty acids and carbohydrates. These produce a lot of carbon dioxide. Now, carbon dioxide, as we already talked about, can initiate the Bohr effect by becoming carbonic acid and lowering the pH. But CO2 also does another thing to promote oxygen release in the promote oxygen release from hemoglobin. That is to form carbamate. So here what we're seeing is the amino terminus of each of the four chains, right? So here we're looking at only one, but this happens at the amino terminus of all four globin chains. And this reacts with carbon dioxide to form something called carbamate. Now this carbamate is negatively charged, right? So it ends in a carboxyl here. And in a similar mechanism to what we saw here, okay, this carbamate stabilizes the T state, right? It makes it harder to switch from T to R. So it reduces the affinity of hemoglobin for oxygen, and so it can deliver more oxygen. You can see that here. So pH 7.4 and pH 7.2, like we saw before, the curve shifts to the right, right? So that's the red and the blue line, respectively. If we're now at pH 7.2 and we add carbon dioxide, the curve shifts even more. So this isn't even taking into account the Bohr effect from carbonic acid. This is simply the effect of carbon dioxide in general. Notice how much more oxygen we can deliver. Now at low pH and at 40 torr CO2, we're delivering 88% of the total amount of oxygen that can bind to hemoglobin at 100 torr, right? So we're delivering 88%, which is great, right? Now remember, the best case scenario we could have had from a non-cooperative, non-allosterically regulated enzyme like myoglobin, the best possible case scenario was 38%. But now we have a tissue that's really pushing itself, generating a lot of lactate, a lot of carbonic acid, and a lot of CO2. We're able to deliver 88%, meaning that now oxidative phosphorylation can continue, which we'll talk about in chapter 18. So we see that hemoglobin is really an exceptionally good electron or oxygen carrier. Oops. All right, so I just want to finish off talking about defects in hemoglobin, so blood disease, specifically sickle cell. Right? It's actually a very good podcast from this podcast will kill you. It's about 2 hours long, but if you're at the gym and you want something to listen to, it's actually very good. If we look at sickle cell anemia, what we're describing is, well, here we have healthy red blood cells. And these healthy red blood cells look kind of like a donut. Of course, everyone knows what a red blood cell is. But in individuals with sickle cell anemia, their red blood cells don't have these shapes. In fact, they're sickled, right? So look like a C or a sickle. That's where it gets its name from. So how do they sickle, and why is this detrimental? First, this cell shape only occurs at low oxygen partial pressures, right? So if we're in our lungs, an individual with sickle cell anemia might have red blood cells that look like that, but once that red blood cells gets to our extremities, let's say our fingers or our toes, somewhere where the partial pressure of oxygen is low, that induces a change into this sickle cell shape. And how does that work, right? Well, that is done through the action of hemoglobin itself, specifically HbS, right? So we have HbA, which is adult hemoglobin, HbA, which is fetal hemoglobin. HbS, the sickle hemoglobin, has a single mutation that allows the formation of these long polymers of hemoglobin, right? And the reason this is so detrimental is that these sickle cell shaped red blood cells are stickier on the outsides, right? So they're the proteins that are on the outside of the sickle cell shape interact better with, say, the walls of our capillaries and of our veins, right? So they stick there, increases the chance of clotting, okay? Additionally, these can kind of grip because of their shape, right? So they can kind of get stuck, and they can actually prevent the flow of blood entirely to our extremities, right? Causing a lot of pain, and in some cases, death, right? So, how do these HbS molecules form these polymers? It's the polymers that are going to give the cell its sickle shape. Well, if we look at here, we have a single point mutation, E6V. This is how we talk about mutations. E being the original amino acid, at what position and to which amino acid it was changed. E6V telling us it was a glutamate to a valine, or glutamic acid to a valine. And these two amino acids have very different properties, right? What can you tell me about glutamic acid or glutamate? Describe it. It's negatively charged, right? Remember, it ends in a carboxyl. The functional group ends in a carboxyl, so it's negatively charged. So what does that mean about that residue? Here. It's negatively charged. Ratio. Yeah, you. It's negatively charged, so what does that tell you about that residue? One thing.
It's hydrophilic.
It's polar, right? It's hydrophilic. So that's fine to be on the surface. Okay? Now valine, on the other hand, is nonpolar, right? It's a branched nonpolar amino acid residue. So what happens? Well, now here we have this valine at position 6. Position 6 happens to be on the surface of the beta chain of hemoglobin, right? So what happens now? Well, coincidentally, there's another barely accessible hydrophobic region on the surface of the beta chain of hemoglobin. That's made up of phenylalanine at position 85 and a leucine at position 88. So we have this little hydrophobic area here. Normally that doesn't do anything. But now, at position 6, right, we have a valine, and this is really unfortunate because at this specific position, right, this beta chain can interact with phenylalanine and leucine on another beta chain on a separate hemoglobin tetramer. And because each hemoglobin has 2 beta chains, well, now we have an interaction here through hydrophobic. We have an interaction now possible here to another beta chain down there, and so on, right, over here as well and over there as well. So what we see then, okay, is something that looks like this, right? A deoxy hemoglobin S aggregate, right? Because again, this is only accessible in deoxyhemoglobin. I didn't remember those sickle shapes only form when oxygen concentration is low. When oxygen concentration is low, now these all stick out, right? And these all interact with each other. So here we have our valine at position 6 in blue and our phenylalanine at position 88 over here, right? So these fit together like building blocks, and this leaves another phenylalanine on this beta chain, which can interact with another one, and so on and so on and so on. so on. So we get these long chains, these long polymers of hemoglobin S, HbS, and these long polymers cause the sickle cell shape to happen. There's nothing inherently wrong with this, except for the fact that A, these can't carry oxygen because they're deoxy, they stabilize the T state rather. Okay, they can't bind oxygen, and for all the reasons we talked about before, these sickle cell shapes cause a lot of downstream problems just by virtue of being, more sticky and causing blood clots and things like that. Right? I won't get into the benefits of sickle cell shape. But anyway, all right, so that's good. We'll on Friday.